To prepare for the distribution theoretic part of this course, we're going to take a quick look at binomial distributions. The example we're looking at here is a coin that has been engineered to have an outcome of heads 60% of the time, which we could consider a magician or even a con artist to be interested in having this coin for gamblers to use. Now, a customer ordered this coin and did a trial of 10 flips, and in those 10 flips she saw that it came up heads 3 out of 10 times, so that would be 30% of the time. We're interested in looking at the hypotheses, testing the question of whether or not we have evidence that this is in fact weighted the way the manufacturer claims it is weighted, or if it is a lower probability than that. Perhaps it's a fair coin at 0.5, something we suspect that it might be closer to a fair coin. And of course, our alternative hypothesis is not really based on our sample statistic of 30%. It's based on the customer having an engineering background and knowing that it's very difficult to design a coin that is unfair on coin flips. Coin spins is a little bit easier to manage, but coin flips are very difficult to make a coin come up any different from 50% of the time as declared heads or tails. So these are our hypotheses. The null hypothesis that the weighting really is the 0.6 claimed by the manufacturer, and the alternative hypothesis that it is closer to being a fair coin than that, so we would think maybe around 0.5, but in particular less than 0.6. To get into the binomial distributions, we first need to establish some basic probability language and properties. So when we say P of A with the A in parentheses like this, first of all, we want it understood that that means the probability of the event A. So in this case, P of heads refers to the probability of flipping heads, and we're going to assume that all of these calculations are just based on the null hypothesis assumption of 0.5. So based on that assumption, the probability of an outcome of tails is just like the probability that the heads does not occur, right? So we would say the probability of tails is equal to the 1 minus the probability of heads. And intuitively we know that if it's going to come up 60% of the time as heads, it's going to come up 40% of the time as tails. But we want to be able to calculate this even when the numbers are a little bit less intuitive. So this would be 1 minus 0.6, which is 0.4. So that was our first probability rule, and this is sometimes what we call complement. Meaning everything but the event that is described here, right? So tails is really the only other possibility in this case, so what we're really asking is anything other than heads. Our second probability rule states that if two events are independent, like 2 flips of this coin would be independent of one another, knowing how it came up on one flip doesn't really impact how I think it's going to come up on the next flip once it's established what the probability is of coming up heads each time. So 2 consecutive flips are independent events. We would say that the probability of A and B, specifying 2 different independent events, we would get by multiplying the 2 probabilities. So the probability of 2 outcomes of heads out of 2 flips is really saying like probability of heads and heads. Which of course is the probability of heads times the probability of heads, or 0.6 times 0.6, which is 0.36. We can also figure out the probability of the sequence HT. That would be heads followed by tails, which would be the probability of heads multiplied by the probability of tails, which comes to 0.24. And finally, the sequence TH equal likelihood is the sequence HT, so we could give a very similar argument and get that that would also be 0.24. So for independent events, we can multiply the probabilities to calculate the probability of an AND. For an OR, we need them to be disjoint events. What it means for two events to be disjoint is that it's not possible for both of them to happen. So, to answer this question about the probability of exactly one head from two flips, we can see that the two ways to get exactly one head are either we had the sequence HT or we had the sequence TH, and we can also see that it's not possible to get both of those sequences. There is no overlap in those. We can't have both of them, so it does make sense to add those two probabilities together. So we're going to say 0.24 plus 0.24 equals 0.48. So there's a 48% chance of getting exactly one head from two flips. Now, if we want to look at the probability of getting at least one head, this gets a little bit more complicated. We have to enumerate the ways to get at least one head. So HT is one of those because that has one head. TH is one of those because that has one head. But the other one that we didn't put into the previous calculation is HH, because that also has at least one head. There isn't any other way to get at least one head from two flips, so this pretty much covers it. And also there's no overlap in these. It's not possible to get the sequence TH and the sequence HH out of the same two flips, so we can add all three of those probabilities together. The probability for HT we decided was 0.24. The probability for TH we decided was also 0.24. And the probability for HH we decided was 0.36. So adding these three together, we get 0.84. This is the kind of combination that's behind the formulas involved in a binomial distribution. As far as what we are going to be held responsible for, we'll make sure that's very clear as we go. We will see some calculations that are a little bit more involved than what we're going to ever have to do by hand, just because they go into the binomial distribution, but we will stick with fairly simple probabilities involving ANDs of independent events and ORs of disjoint events for our own assessment purposes.